So it's June 2018 Unified Chemistry paper. So let's whiz through these short answer questions. So first of all, the element that forms a -1 ion with the same electronic configuration of helium. So helium is 1s2, so we're looking for an element that has the electrical configuration of 1s1 because it needs to gain an electron to get to 1s2. So that must be hydrogen. The element with the highest first energy, so obviously the noble gases have the highest first energy as you go in the periodic table, but they get lower as you go down the group, so therefore the highest one must be helium. The element in period 3, so period 3 goes from sodium to argon, which has those successive ionization energies. So you're looking for a big jump, and you can see the big jump occurs between the second and the third. So it must be the element which is in group 2, period 3, and that's magnesium. Element that forms a compound with fluorine that has octahedral molecules, that is of course sulfur. You would have done that as part of your shapes of molecules, SF6, octahedral. Element that reacts with water to form an acidic solution, that is chlorine or fluorine. You would have done that in group 7 chemistry. Element which forms a compound with hydrogen of XH3 with a molar mass of 34. So if you take 34, you minus your 3 hydrogens, you get to 31. So you look for the element which has a relative atomic mass of 31, and it is phosphorus. Element that forms a compound with hydrogen in which the element has an oxidation number of -4. That is going to be methane, the compound methane, so the element is carbon. And finally, the element which has a density of 1.33 times 10 to the -3 grams per centimetre cubed at room temperature and pressure. So because it's at room temperature and pressure, and you know that any gas has a 1 mole occupies 24,000 centimeters cubed. So you times this number by 24,000, and that will give you your molar mass, and that is 31.92, which will be O2. So the element is oxygen. So we need to look now at these chlorides and explain their properties. So you will know, of course, well, you can look at the melting point, but you'll know that sodium chloride and magnesium chloride, they are both going to be giant ionic structures, and you can tell that they have a very high melting point as well. For these four, these are going to be simple covalent molecules because the melting points are low and electrical conductivity is poor for both the solid and the liquid. So you just need to explain those properties, which I've done below, and that's pretty nice question really for 5 marks. Just remember you've got London forces between the molecules for these guys here. And ionic bonds are of course much stronger than London forces, which results in the higher melting points. So again, this is quite a nice little question for you. The first one, you are plotting a graph, and the other page here I've shown kind of scale that you could use. You then draw your tangent at 500 seconds, and you should get a tangent of between these two figures here, which shouldn't be too difficult. You're now going to work out the concentration of your hydrogen peroxide that you started with. So they tell you worked out, you ended up with 55 centimeters cubed of oxygen at room temperature and pressure. And again, that means that you can use the equation of moles of gas equals volume in centimeters cubed divided by 24,000. So moles of O2 is here. Then you'll notice that for every 1 mole of O2 formed, you need 2 moles of hydrogen peroxide. So you need to times that by 2 here. And then finally, your original volume of hydrogen peroxide was 50 centimeters cubed. So you work out your concentration by moles, divided by volume, times by 1,000 to give you 0.092. Notice they wanted it to 2 significant figures. Then for part B, we are going to combine these two equations. You need to work out which equations you're going to use. So it wants you to write an equation where hydrogen peroxide acts as a reducing agent, which means that the hydrogen peroxide must be oxidized. So we are looking at this equation here for that, because if it needs to act as a reducing agent, it needs to release electrons like so. And you'll notice that for this equation here, where you start with hydrogen peroxide to go there, hydrogen peroxide is actually acting as a oxidizing agent because hydrogen peroxide is being reduced here by gaining electrons. So that's why I am using this equation here. And then you notice that the standard electric potential is 0.68 volts. So you were looking for a half cell which is more positive than that, because the half cell needs to be more positive so that this one gets reversed. The only one is going to be this one here, which is Mn04 minus being reduced to give you Mn2 plus. You then need to make the equations balanced. So this one you need to times by 5, so you get 10 electrons. This by 2, so again you get 10 electrons, and then you combine them. When you do that, you notice that you end up with 10H plus on this side and 16H plus here. So that cancels. So that goes as well. So that gives you your final equation. So the first thing we need to do here is write an equation for experiment 1, which I've done there. I'll just put the colours there just so you can see. Look, for experiment 1, it changes from pink to blue. So you need to start with your octahedral complex and end up with your tetrahedral complex. Okay, and then it asks you to explain the observations for experiment 2. So it tells you that you cool it down, and the reaction changes in colour from blue to pink. So as you'll know from Le Chatelier's principle, that if you cool a reaction down, the equilibrium will shift in the exothermic direction, which is what I've shown here. And therefore the forward reaction, which is that one, must be endothermic, because the reverse is exothermic. Okay, so we now need to draw some optical isomers. I've drawn one, and I'm just going to show how to draw these in the easiest possible way. So the first way is to draw your central metal ion and then put your octahedral bonds around. Now, oxygen is the ligand that you need. So there you go, put some oxygens in. Now we're going to do the reverse. So you'll notice this one, so that goes that side, that goes there, and that goes there. And then finally put on your double bonded oxygens like so. And then the final step is to just put your charge on like so. So on the next page, they're going to ask us for the colour change to mark the endpoint for this question. Now, they told us that cerium 4 plus is yellow and cerium 3 plus is colourless. But the key thing to notice is that this is in the burette, which they've told me here. So that means that in my burette, like so, my solution is going to be yellow. As it hits the conical flask here and reacts it is with the ethane dioic acid, it is going to go colourless. However, once all of this is used up, the yellow colour will no longer disappear, so it will stay yellow, and therefore the endpoint is when it goes from colourless to yellow. Right, so we now need to work out the calculation for the titration. So I put the titers there, and as you can see, the number 2 is too far out, and therefore that one needs to be ignored. So once you've done that, it's just a straightforward titration calculation. So you've got your mean titer here, which you've worked out. to be the average of number 1 and number 2. Then you find your moles of cerium 4 plus, because the concentration they've told you as being 0.05. You need to then divide that number by 2 to find your moles of the acid. That is in 25 centimeters cubed. So you need to then multiply that by 10 to find the number of moles in 250, which is your original volume. Then multiply that by the mass of your acid, which is 90, and then finally work out your percentage by mass of ethane dioic acid in your rhubarb, and you do that to 3 sig fig, because everything else, because you've got, as you can see, your readings, an acid concentration of the cerium 4 plus is to 3 sig fig. Okay, so we're now moving on to look at cisplatin. So first of all, what's the oxidation number of platinum in cisplatin? Well, ammonia, as you know, is neutral, chloride is -1, so for the overall complex to be neutral, platinum must be +2. Then you want you to look at the mechanism for this reaction here. So you can see that one of the chloride ligands is being replaced by an ammonia ligand here. Ammonia, you know that a ligand is a lone pair donor. So in comes ammonia to donate its lone pair to platinum here, and that means that the chloride must leave. Paracetamol is used as a painkiller. Name those functional groups. So you know here you're going to have a phenol, and here you have got an amide. So now we're going to look at how we go from 4-nitrophenol to paracetamol. So first of all, they want us to include the mass of 4-nitrophenol required, reagents, intermediate, and details of how we would purify our paracetamol. So let's first of all do the calculation. So we can find out our moles of paracetamol, because we need to get 5 grams of pure paracetamol. Molar mass of paracetamol is 151 to give you 0.0331. You need to scale that up, because going from here to here is only a 40% yield. So to go backwards, you need to multiply by 100 over 40 to get your moles of 4-nitrophenol. And then to find your mass of 4-nitrophenol, you times it by the molar mass of 139 to get 11.5 grams. Stage 1, you need tin and concentrated HCl. Your intermediate is this guy here. And to purify, you are going to use recrystallization. So for recrystallization, you dissolve the solid in a minimum amount of hot solvent. You then cool the solution down and filter the solid off, and then you will wash with cold solvent and dry. Okay, so now we're going to go on to some enthalpy, an enthalpy calculation. So again, this is AS chemistry, so it's not too bad. So the first thing you do is work out your the energy released during the reaction. So you've got 50 centimeters cubed of the acid here, and 50 centimeters cubed of sodium hydroxide. So your total volume of water, or your total mass of water, is 100 grams. Times it by your specific heat capacity of water, which will be on your data sheet, and by your temperature change, which is 5 degrees, to give you 2090 joules. Moles of acid you can work out. You've got 50 centimeters cubed of 0.4 moles of it to give you 0.020 moles of it. Then convert this to kilojoules, which gives you 2.090 kilojoules. Divide it by 0.02 moles to give you your delta H. But they want delta H neutralization, and remember, delta H neutralization is the formation of 1 mole of water. For this, you form 2 moles of water, so you then need to divide that number by 2 to give you minus 52.25. Why is it a minus? Well, it's a minus because your temperature went up, and therefore it's an exothermic reaction. So we move on to some Kc calculations now. So how could I determine the equilibrium amount of succinic acid? So you use titration for that, acid-base titration. Write an equation for the equilibrium that takes place. So the key thing here is obviously these are your reactants, and notice that you have got here 2 moles of ethanoic acid. So you need to put your of ethanol. So you need to put your 2 there. And you also form 2 moles of water there, so you need a 2 there as well. Okay, so the skeletal formula of the acid present of the ester that you've made. So I've drawn the succinic acid there. This is then going to be completed that you put 2 ethyl groups on the end there. Why can we use expression 5.1? So why can we use the number of moles rather than concentration, which is of course what we should use for Kc? That's because you've got 3 terms up here, 3 terms there, so they cancel, the volume will cancel. Now I'm going to calculate Kc for this reaction. So I've put the initial volumes that I start with here. So it tells me that I form 0.0200 moles of succinic acid present in the equilibrium mixture. So I've got that. That's been reduced by 0.03. So that means the ethanol must be reduced by 0.06 because for every 1 acid you need 2 ethanols. And then you're going to produce 0.03 moles of the ester and double the amount of water. Then you just pop those expressions into Kc and you get 0.667. And of course there were no units for that because the units cancel as well. So, final question. First of all, we need to name compound A. So, as we look at the carbon chain, we've got 4 carbons there, and it's an aldehyde here. So, we start with butanol, then we've got a hydroxy group on carbon number 1, 2, 3. So, 3-hydroxybutanol. What type of reaction is this? Well, you take 2 molecules and you make 1, so it's addition. Reaction 6.1 takes place in 2 steps. First of all, your ethanol reacts with hydroxide ions as an acid-base reaction. So they want the conjugate acid-base pairs. So hydroxide is going to be your base. So that's going to remove a proton from your ethanol. It doesn't really matter which one you remove. I've just removed one. I've removed this one, for example. You're obviously going to get a minus charge and water. And then you need to suggest the equation for step 2. So you need to use your other ethanol. You need to then use up both of the terms, both of these, because they do not appear as products in your overall equation. That would then make your product, and then you need to regenerate hydroxide ions because they've told you that hydroxide ions act as a catalyst. You've used them in step 1, so you need to regenerate them in step 2. Right, so this next one's a little bit tricky. So I'm now going to start with propanone, and it wants me to give you the structure of the organic product. So I've drawn compound A, and you can see compound A. Hopefully you can see this bit is just this bit here, and then this bit is going to be this bit here, but it's it's going to be let's change that. It's going to be the whole molecule, isn't it? It's going to be this bit here. But that has then changed for an OH, and then that and it's added across. So when I change this for propanone, this is going to become a CH3 group, and this here is going to become a CH3 group. So on the same molecule, if you just carry it forward, that will be a CH3 group, and that will be a CH3 group. So when you come to do your product, you just remove that, and then this becomes CH3, and that becomes CH3, like so. That's tricky. Really, this next question is a bit of a gift, isn't it? If you know your organic chemistry. So it wants us to explain the roles of electrophiles in organic chemistry, including one reaction of an aliphatic and one reaction of an aromatic compound. So I've shown that below. So the first one I have shown is going to be electrophilic addition of an alkene, bromine across an alkene double bond, giving you the mechanism and the product. The next one is the electrophilic substitution to form nitrobenzene. And I've also shown how you regenerate the catalyst here, so how you form your electrophile there to give you a detailed explanation, which is what they would want. And that is about what they like really. You could say that an electrophile is an electron pair acceptor as well. So electrophile, electron pair acceptor, and I think then everything's in.